Welcome back. So today we're going to talk about a new topic, which is randomized algorithms. So we're going to spend the next 4 or 5 lectures on randomized algorithms. And one reason is that these algorithms are very interesting. And another reason is that many important algorithms used in practice are randomized. Okay, so to give an outline of today's lecture, I'm first of all going to introduce what randomized algorithms are, and then we'll do a brief review of basic probability theory, which we need in order to analyze randomized algorithms. And then we'll look at 2 simple applications of randomized algorithms, which is max cut and quicksort. And then we're going to look at another problem, which is hashing. So you've probably seen some sort of hashing before. So you might have seen close addressing hashing. But today we're going to talk about 2 other forms of hashing, universal hashing and perfect hashing, which might be new to you and which you might find interesting. Okay, so first of all, what are randomized algorithms? Well, until now, most of the algorithms we've talked about have been deterministic. And what that means is that, so for a deterministic algorithm, if you give it one particular input, the algorithm is always going to do the same set of steps, and it's always going to produce the same output. Okay, so one input produces one output. Okay, always the same output. However, it turns out that sometimes it's useful to allow algorithms to be non-deterministic. Okay, so for example, as the algorithm operates, then perhaps we can allow the algorithm to do some random actions. Okay, so maybe it can flip a coin, or it can roll a dice, or somehow it can generate a random number, and then its behavior can be guided by those random choices. And so because the algorithm is allowed to make random choices, then if you run the algorithm several times, even on the same input, the algorithm can produce different outputs. Okay, so the algorithm is no longer deterministic. So now it's a non-deterministic algorithm. Right? Okay, so the one question you might have is, why should we consider randomized algorithms? Okay, because usually, if I ask you to solve a problem, you're going to follow just a fixed procedure, and you're not going to just go do a bunch of random things, right? It seems kind of strange to want to do some random things in order to solve a problem. But as it turns out, randomized algorithms actually work very well in practice. Okay, in fact, oftentimes they work better than deterministic algorithms. So for example, randomized algorithms might be faster than deterministic algorithms, okay, or they might use less memory. The randomized algorithms are often quite simple to explain how they work. Okay, so you might have some very complicated deterministic algorithm to solve a problem, but if you use a randomized algorithm for the same problem, it's sometimes much simpler and much easier to understand what the algorithm is doing. Okay, that doesn't mean that the algorithm is necessarily, it might be difficult to prove the algorithm actually works correctly. Okay, but simply to state the algorithm is often much easier for randomized algorithms than deterministic ones. Okay, and in fact, there are some cases where we have problems that can be solved efficiently by randomized algorithms, but you can actually prove that no deterministic algorithm can solve the problem as efficiently. Okay, so sometimes randomized algorithms are the only way to solve a problem efficiently. And finally, if you look at this picture down here, so these are like the the orbitals of electrons in quantum mechanics. Okay, so quantum mechanics is basically our sort of our best way to describe the universe that we live in. Okay, and quantum mechanics is inherently probabilistic. So there are many phenomena in quantum mechanics which are randomized. Okay, we have no way of predicting exactly what they do. So in that sense, our universe is in fact random. Okay, so there are random choices being made in our universe. And so, so therefore, if we want to solve problems which are relevant to our universe, right, which are relevant to our lives, then it makes sense to consider these randomized algorithms. Okay, so let's give some examples where it's actually useful to have randomness. All right, so the first example is a very simple problem. So suppose you have a string, okay, of length n, and so let's say half the string. The string is going to have letters A and B in it, and let's say half of the letters are A and then half of them are B, okay, but they could be in any order. So for example, the string could be like AABB, or it could be like ABAB, or any other order. Okay, so and then all we want to do is we just want to find one location in the string which is an A. Okay, so just find any A in the string. Now, if you use a deterministic algorithm, okay, then this algorithm is going to go through the string in some sequence, right? So maybe it's going to look at the first letter and then the second letter and so on. Okay, or it could do something else. Maybe it's going to look at the 7th letter, right, and then the 5th letter, and then the 29th letter, or something, right? But it's going to follow some fixed pattern in order to look through the string in order to find an A. And now what can happen is that whatever order the algorithm decides to look through the string in, okay, we can always make the first half of the letters that the algorithm looks at, we can make all of them be B's. Okay, so we have n letters in total, and we can make the first n/2 letters that the algorithm looks at all be B's, right? And this is because the algorithm is deterministic. So therefore, we can, the first location that the algorithm looks at is fixed, right? Okay, so we can make that be a B. Okay, and then after that, the algorithm is going to see that, well, okay, the first location is a B, so then it's going to pick a second location, and that second location is also deterministically chosen, okay, because we can guarantee that, so we can force the algorithm's first location to be a B, and so that way we can predict what the algorithm is going to look at for the second location, all right, and then now we can make that also be a B, right, and then the third location that the algorithm looks at, that's simply a deterministic function of the first two locations it looked at, okay? And we can guarantee that both of those are B's, so therefore we know what is the third location the algorithm will look at, and we can force that to be a B also, okay? So we can just keep doing this, and then we can do this for, so we can make all of the first half of the letters the algorithm looks at be B's. So therefore, any deterministic algorithm, okay, is going to take at least n/2 plus 1 steps in the worst case. Okay, this is true for any deterministic algorithm. Now, on the other hand, if you consider a randomized algorithm, okay, so randomized algorithm, well, so let's say the algorithm is just going to look at a random location in the string. Okay, so it's not fixed what location the algorithm looks at, right? It's just going to flip a coin or somehow get some sort of randomness input, right? And then it's going to go look at a random location in the string. Okay. Well, now there's since half the string is A's and half of it is B's, right? Then there's a 1/2 probability that the location that the algorithm looks at is an A. Okay, right? And so therefore, since there's a and if it's not an A, then the algorithm is going to look at a second random location. Okay, so the algorithm is just going to keep checking random locations. And so therefore, since each time it checks a location, it's got a 1/2 probability of finding an A, then in expectation, the algorithm only needs to take 2 steps before it finds an A. Okay, and this is compared to the deterministic algorithm, which we can always force that algorithm to take n/2 steps. Now, of course, it's possible that this randomized algorithm also takes more than 2 steps, right? So maybe it gets unlucky, and then for all of the locations it checks, okay, they're always B's, right? So this is possible, okay? So, but it's very unlikely that this happens, right? So in the average case, this randomized algorithm will only take 2 steps. Okay, so that's one example where randomness is useful for us. A second example would be, now suppose we have a problem like, I give you a shape of some sort. Okay, so this is just a very complicated shape. We don't really know how it's defined, but I just give you the shape, and then I ask you to measure the area of this shape. Okay, so now if you use a deterministic algorithm, right, then you're going to have to go through some pretty complicated procedure in order to find the area, right? So maybe you can do some sort of integral of some sort, right? So in fact, so here I'm showing a 2D shape, but in general you could have a higher dimensional shape. Okay, so this could be like a 3D shape or a 3D structure, or it could even be like, you know, a 1,000-dimensional structure, right? So then, you know, as the dimensionality goes up, the algorithms to find the area or the volume are also going to get more and more complicated. Okay, so that's for the deterministic algorithm. On the other hand, for the random algorithm, okay, this is going to be much simpler. So, so one thing that you can do is you can just take the shape, right, and then you can print it out on a piece of paper, okay, and then you can maybe throw a bunch of darts at it. Okay, so you randomly throw a bunch of darts and they're going to hit random locations on your piece of paper. And then you're just going to look at what percent of the darts that actually land on the paper, right? What percent of them actually are in your shape? Okay, so for example, you know, if you made a, let's see, so is this the pen right now? Yeah, okay. So if you printed out the shape, right, on this piece of paper, right, and then you throw a bunch of darts, right, maybe some of them are going to hit the shape and some of them are not. And then you're just going to look at the percentage that hits. Okay. And then you're going to multiply that by the area of your piece of paper. And that tells you approximately what the size of this shape is. Okay. And this works even in higher dimensions. So in fact, the only thing that you need for this procedure to work is that you need some way to create random locations in this overall piece of paper or this volume that you're considering, right? And then also you need to know for each of those random samples whether it lies within your shape or outside of your shape. Okay, so those are the only two things that you need to do. And once you have that, then you can use this randomized procedure to get the approximate volume of the shape. Okay, so those are two simple examples where randomness can be useful. And so hopefully these convince you that you know, there's some value to considering these randomized algorithms, and that for some problems, they can really be much better, right? Either more efficient or much simpler than the traditional deterministic algorithms. Okay, so now before we look at these randomized algorithms, I just want to introduce some terminology. So, so we actually have two types of randomized algorithms. We have Las Vegas algorithms and the Monte Carlo algorithms. Okay, so both of these are randomized, but the difference is that the Las Vegas algorithm is always going to produce the right answer. Okay, so it's going to make some random choices, but in the end, this algorithm is guaranteed to produce the right answer. Okay. However, the running time of the algorithm can depend on the random choices that it made. Okay, so therefore, this algorithm can run for different amounts of time on the same input. Okay, it's always going to have the right answer at the end, but sometimes it might run quickly and sometimes it might run slowly. And so, so what we want for these algorithms is to minimize the expected running time of the algorithm. Okay, so even though the algorithm might run for a long time, in some cases, we want the probability of that happening to be very small. Okay, now for the Monte Carlo algorithms, okay, these are like the opposite of the Las Vegas algorithms, in the sense that they're always gonna have the same running time. Okay. However, sometimes this Monte Carlo algorithm might give you the wrong answer, okay, depending on the random choices that it made. Okay, now, of course, we don't want the wrong answer, so when you have a Monte Carlo algorithm, your goal is to minimize the error probability of the algorithm. Okay, so yeah, and so in today's lecture, in the next few lectures, we're going to look at different algorithms, and some of them are going to be Las Vegas, and some of them are Monte Carlo. Okay, so before we do the algorithms, let's just do a basic review of probability theory. Okay, so I'm sure you guys have all seen this before, but you know, in case you haven't looked at this stuff for a few years, then let's just do a basic review. Okay, so since we're working with combinatorial algorithms, right, we're usually working with like finite sets of elements, then we're going to be talking about discrete probability theory, okay, as opposed to continuous probability theory. Okay, so in discrete probability, we have these things called events, right? And events are going to happen with certain probabilities. And events can also be composed of other events, right? So we can have basic events and we can have more complicated events. So, so for example, if you have a die, right, like a 6-sided die, okay, then one possible event is you roll the die and you get a 2, okay, and then this happens with a certain probability, so it's going to be 1/6 if your die is fair. Okay, you could also have more complicated events like the event of rolling an even number. Okay, so so this means that you either roll a 2, a 4, or a 6. Right? So those are the more basic events which make up this more complicated event. Okay, and then this is going to happen with probability 1/2. Okay, so if A is an event, then we're going to have this notation. So the probability of A equals Y. Right? So for example, the probability of rolling a 2 is going to be 1/6. Okay, now we're going to say that, so here's an important notion, which is that events could be independent of each other. And so intuitively, this means that one event happening does not affect whether or not another event occurs. So more mathematically, we're going to say that two events A and B are independent if the probability that both A and B occur is equal to the probability that A occurs times the probability that B occurs. So for example, so if A is the event that I roll the die and then I get a 2 on the first roll, okay, and then a B is the event that if I roll the die again, I get a 3 on the second roll, okay, then these two events are independent of each other, right? Because whether or not I got a 2 on the first try doesn't affect whether or not I'm going to get a 3 on the second roll. Okay, and to see this, you can see that the probability that I get both a 2 on the first roll and a 3 on the second roll, right? Well, there's only one way for this to happen, right? On the other hand, there are 36 ways in total, 36 possible outcomes for rolling the dice twice, right? Because there are 6 sides. Okay, so therefore, the probability I get both A and B is going to be 1/36. Okay, and this is equal to the probability I get an A on the first roll, which is 1/6, times the probability of B, which is also 1/6. So therefore, these two events are independent. Okay, now for events, as an example of events which are not independent, suppose A is now I get a 2 on the first roll, and then B is that the sum of 2 rolls is going to be 5. Okay, so now you can kind of see that A is not independent of B. Right? Because if A happened, then the only way for B to happen is that I have to get a 3. I have to roll a 3 on the second roll. Okay, and to see this mathematically, we have that the probability that both A and B occur. Okay, this is 1/36, right? Because because I have to get a 2 on the first roll and then a 3 on the second roll. Okay. On the other hand, the probability that A occurs times the probability B is going to be 1/6, right, times 4/36, right? Because if I roll the die twice, then I have 4 different ways for the 2 rolls to sum up to 5. Okay, and so these two things multiplied together are not equal to the probability of A and B, and so these two events are not independent. Okay, so next we have random variables. Okay, so random variable is just a variable which can take values with certain probabilities. And then if you sum these probabilities over all the values that this variable can take, that sum has to come out to 1. Okay, so for example, if x is a random variable representing the value that you get when you roll a die, okay, then the possible values are 1 through 6. Okay, and each of these events happens with 1/6 probability. So another random variable is like suppose I flip a fair coin 4 times. Okay, then I can look at the number of heads I get. Right, so the value here can be 0 to 4 because I can get anywhere from 0 heads to 4 heads. Okay, And the probabilities are going to be these numbers. Okay, so I'm not going to calculate all of these numbers, but basically, if I get 0, if y equals 0, then that means I get no heads. I get 0 heads after flipping 4 times. Okay, and the probability of this is just 1/16. Okay, and you can also calculate the other probabilities. Okay, and then you can also, so you can define, for example, z to be the number of flips of a coin until you hit the first head. Okay, so now the values are going to be 1, 2, 3, and then so any value. Okay, so z can be any natural number. Okay, any positive natural number. Okay, and the probabilities are going to be, well, if z equals 1, then that means that you flipped once and then got a head. Okay, and this happens with a 1/2 probability. Okay, or maybe you needed to flip 2 times to get a head. Okay, and this happens with 1/4 probability. Right, to flip 3 times to get your first heads has 1/8 probability, and so on. Okay, and then if you sum up all of these probabilities over here, right, 1/2 plus 1/4, and so on, you're going to get 1. Okay. Right. Okay. And then when you have random variables, we're going to use this kind of notation. We're going to say that the probability that this random variable, capital X, equals a particular value, little x, okay, is going to be equal to some value y. Okay, so for example, the probability that I need to flip the coin 3 times till I hit the first head, okay, is going to be 1/8. Okay, so once we have these random variables, then we can define the expectation of a random variable. Okay, so the expectation is just going to be the sum over all possible values of this random variable. Okay, so x can take some set of values, possibly an infinite set of values, but we're going to sum over this entire set of possible values for x. Okay, and then for each of them, we're going to look at that value, little x, times the probability of getting that value, little x. Okay, and we sum this over all possible all possible values, little x. So this is kind of like the average value of this random variable. Okay, yeah. So if you take like a random instance of this variable, right, then what do you expect to get? So that's the expectation of that random variable. Okay, so for example, if you flip, so let's say that x here, this random variable, is the number of heads you get in 4 flips. Okay, well, so we know that if the coin is fair, right, then we expect to get like 2 heads out of 4 flips. Okay, and to compute that, we can actually do the sum. So the possible values for x are anywhere from 0 to 4, right? And so we're going to multiply each of these values, each of these little x, by the probability of getting that value. Okay, so for example, the probability that you get 0 heads is 1/16. The probability that you get 1 head is 4/16, and so on. Okay, so we can write out this entire sum, and we're going to find that indeed the sum is going to come out to 2. Okay, meaning that on average you're going to flip the coin. On average, if you flip the coin 4 times, you're going to get 2 heads. Okay, so yeah, so if you do this 1,000 times, then probably you're going to see 2 heads for each of your 4 flips. Okay, now we have a special type of random variable, which is an indicator variable. Okay, so an indicator variable for some event. Okay, so we have an event E, and then for that event, you can define an indicator variable for this, and this is going to be 1 if that event occurs, and 0 otherwise. Okay, so this indicator variable only has two possible values, 0 or 1, indicating whether E occurred or not. Okay, and if this event E has a probability P of occurring, right, then what is the expectation of its indicator variable? Well, the expectation is going to be equal to P. Okay, and the reason is simply that the expectation of this random variable is just, so this random variable can either be 0 or 1. Okay, so when it's 1, then that means that E occurred. right? Sorry, that X occurred, okay? Or sorry, E occurred, okay? So E occurs with probability P, okay? So we have a P times 1 here. And then also, if E doesn't occur, then this variable has value 0, right? So overall, this sum here is going to be P. Okay, so this is just like a convenient fact, and then we're going to use this fact to simplify some of our calculations later. Okay, so one more fact that we need. So this is called linearity of expectations. Okay, so this is quite important because it makes our life much, much easier when we analyze randomized algorithms. Okay, so the linearity of expectations is saying that suppose we're given two random variables, x and y. Okay, then we can just add them together and we can get another random variable. Okay, and then we can look at the expectation of that sum. Okay, so the expectation of x plus y. Okay, and it turns out that this expectation is equal to the expectation of x plus the expectation of y. Okay, so this is kind of intuitive and kind of natural, right? But it's still it's kind of amazing how often we can use this idea, okay, to make our lives much, much easier when we work with randomized algorithms. Okay, so it's both a natural principle, and it's also kind of unexpected in terms of how useful it is and how general it is. All right, so this linearity of expectation actually extends to any number of random variables. Okay, so you don't just have to have two random variables. You could have like 3 or any number of random variables. But in any case, the expectation of the sum of these random variables is always equal to the sum of the expectations of the individual variables. Okay, and one thing that makes this idea so useful is that these variables, we have very few restrictions on these variables. Okay, in particular, we do not require these variables to be independent of each other. Okay, so y can depend on x, but this linearity of expectations still holds. Yeah, so it's a very useful property. And just to give an example of this, so suppose we want to compute the number of heads. So we're going to flip a coin 100 times, and you want to compute the expected number of heads. Okay, so x is equal to the actual number of heads. We want to compute the expectation of x. Okay, well, if we just use the direct definition of expectation, right, then what we should do is, I guess there should be like a 0 here, but we can take that out because it's going to be 0 times something. Okay, but what we can do is we can look at the probability of getting one head, right, times 1. Okay, because it took you 1 flip. Okay, plus if it takes you 2 flips, then you do 2 times the probability of 2 times the probability of getting 2 heads. Okay, and so on, and then you can do the sum for all of the possibilities. Okay, all 101 possibilities, right? And so the problem with doing this is that each of these individual terms is going to be quite complicated. Okay, so for example, the probability that you get 2 heads. Okay, so this is going to be basically 100 choose 2. Okay, and you have to multiply that by 2, and then you have to add that for all the other probabilities. Okay, so it's a very complicated sum that you have to evaluate. However, if we use linearity of expectations, the whole problem becomes much, much easier. Okay, because what you can do is you can say that the total number of heads in 100 coin flips is going to be equal to, I'm going to set this equal to the sum of 100 indicator variables. Okay, each of these, so x sub I is going to be whether or not I got a head on the ith flip. Okay, so it's going to be either 0 if I didn't get a head, or it's going to be 1 if I did get a head on the ith flip. Okay, and so the total number of heads is just the sum of 100 of these indicator variables, right? Okay, and now for each of these indicator variables, it's actually very easy to evaluate its expectation, right? Because in fact, we know that the probability I get a head is just going to be p on the ith flip. Okay, so by the previous fact, we have that the expectation of any of these indicators is just going to be 1/2. Okay, and now we can invoke linearity of expectations, And we can say that the expectation of x is equal to the sum of these individual expectations. And we know that each of these individual ones is just going to be 1/2, right? Each of these individual things is 1/2, and we have 100 of them, okay? And so therefore, the expected number of heads is going to be 50. Okay, so if you did this calculation over here, up here, right, then assuming you did this correctly, right, so that's actually not necessarily that easy to do this sum correctly, but assuming you did this correctly, you would have also gotten 50, okay, but you would have had to do a lot more work. So yeah, so okay, so that's the basic introduction. So now let's look at some simple applications of randomized algorithms. Okay, so the first algorithm we're going to look at is max cut. Okay, so so we actually looked at this when we talked about local search algorithms. Okay, so max cut is sort of like the opposite of min cut. Right? So min cut we talked about when we looked at max flow, and min cut we were trying to take a graph and then break it into two pieces where the number of edges between the two pieces is as small as possible, right? But for max cut, we want to have as many edges as possible between the two parts. Okay, so for example, yeah, and in fact, for max cut, let's say that we want to restrict this problem so that you split the problem into two halves, but each half has to have, let's say, about half of the vertices. Okay, so you don't want very uneven splits, right? You don't want like one side to have like one vertex and the other side to have like all the other vertices. Okay, you want to do a more even split, and then you want to pick one of those even splits that has the most number of cut edges. Okay, so in this example, we would have how many? We would have 6 edges that cross between the two sides. Okay, so we want to make this number as large as possible. All right, now unlike min cut, the max cut problem is actually NP complete. Okay, and so last time we looked at, when we talked about local search algorithms, we looked at an algorithm which could eventually converge to a solution which was a 1/2 approximation. Okay, meaning that if the maximum cut has, let's say, E edges in it, right, then that algorithm would always produce a cut with at least E over 2 edges. Okay. However, we didn't really have a bound on the running time of that algorithm. Okay. In fact, if we wanted to bound the running time of that algorithm, then we couldn't get a 1/2 approximation anymore. We would have to lose an additional factor of, let's say, 1 plus epsilon. Okay. Yeah. Okay. So so now we're going to look at a randomized algorithm. It's going to be a Monte Carlo algorithm, meaning so it's going to be a Monte Carlo 2 approximation algorithm. Okay, so what that means is that in expectation, the algorithm is going to produce an output which is a 2 approximation of the optimal. Okay, so again, if the cut is E, then this randomized algorithm is going to produce in expectation a cut which is at least E divided by 2. Okay, but sometimes this algorithm can actually give you the wrong answer. Okay, so sometimes this algorithm can perform very poorly and give you a cut which is very, very small. Okay, maybe it's like, just 1% of the maximum cut. Okay, but on average, it's going to give you half of the maximum cut. Okay, on the other hand, this algorithm is always going to run in the same amount of time, as we'll see. Okay, so now I said one of the virtues of randomized algorithms is that they're simple. Okay, or many of them are simple. Okay, and this algorithm is basically as simple as you can get. Okay, so here we're trying to find a cut of the graph, right? So we have a bunch of nodes, right? And we want to decide which side they're going to lie on. Okay, right? So we have a bunch of edges between them, right? And the algorithm is just that we're going to go through all of the nodes one by one, and for each node, we're going to put them on a random side. Okay, with probability 1/2. Okay, so we have 2 sides, A and B, right? So maybe this guy goes on side A, right? This guy goes on side B, right? This guy goes maybe on B again, right? This guy is on B, and then A, and then A, and then B, and so on. Okay, so we just iterate through all of the nodes, and for each one of them, we put them either randomly on side A or B with equal probability. And I claim that this already gives a 2 approximation to the max cut. Okay, so to see this, what we're going to show is that suppose you have a graph with e edges. Okay, then this randomized algorithm is going to produce a cut with expected size e over 2. Okay, so yeah, and so of course, given a graph with e edges, the biggest possible cut is going to have e edges in it. Right? At most, you can cut every single edge. Okay. And what we're saying with this lemma is that in expectation, we're going to produce a cut of size e divided by 2. So that's guaranteed to be half the max cut, right? Yeah, so this is why this algorithm is going to achieve an approximation factor of 2 if we can show this lemma, okay? And this lemma is going to be, it's going to have a pretty simple analysis. So let's let x be a random variable equal to the size of the cut. Okay, so we want to know how big this cut is, so we want to bound the expected value of x. Okay, the way we're going to do this is we're again going to rely on linearity of expectations. Okay, so we're going to define x to be a sum. So x here is a pretty complicated random variable, but we're going to decompose x into a sum of many much simpler random variables. Okay, and then we're going to apply linearity of expectations. Okay, so the way we're going to decompose x is that for each edge e in the graph, okay, we're going to define x sub e to be an indicator variable of whether or not e was cut. Okay, so we run this algorithm, right? And that's going to cut some of the edges and not cut some of the other edges. Okay, so for each edge, we're just going to let x of e be an indicator variable for whether or not the algorithm actually cut the edge. Okay. Yeah, so, and then the total size of the cut is just, we're going to look at every single edge, and then it's just the sum of these indicator variables, right? Because every time you have a cut edge, you have this indicator being 1, okay? We just want to count how many edges got cut. Okay, so now, okay, so now what you can say is that if you have an edge ij, okay, so it's got 2 vertices I and j, right? Then this edge is going to be cut if and only if I and j are on different sides of the cut. Okay, right? If I and j are on the same side, then this edge between them is not going to be cut. Okay, so therefore the probability that this edge is cut, is cut, okay, is the probability that I and j are on different sides of the cut. Okay, so there are 2 ways for this to happen. Either I can be on the left side and j on the right side, right? Or j is on the left side and I is on the right side. Okay. Now the first one, this has got a 1/4 probability of happening, right? Right, because I is going to be on a random side, okay, with 1/2 probability, right? And then j is also on a random side. So the fact that I is on the left and j is on the right, this is going to have a 1/4 probability. Right? These 2 events are independent. Okay, and likewise for the other one, for j on the left and I on the right, this is also going to have 1/4 probability. Okay, and of course these 2 events are disjoint from each other, so the probability that either of them happens is just the sum of their probabilities, and this is going to be 1/2. So therefore the probability that an edge e is cut is 1/2. Okay, and so by the previous statement that we had, fact that we had, the expectation of this indicator variable is also going to be 1/2. Okay, and therefore now we can apply linearity of expectations to this equation over here. Okay, so this is saying that the expected value of x, right, which is what we want to compute, right, this is going to be the sum of the so the expected value of x. Sorry, let me write this a bit nicer. So the expected value of x is going to be the sum of the expected values of all of these indicator variables. Okay, but each of these has expectation 1/2. Okay, and since you sum over all of the edges, right, then in total this the value of this capital X is going to be e divided by 2. Okay, where e is the total number of edges. Okay, so this shows that we're going to achieve this this cut, and so this is going to be a 2 approximation, right? Because again, you can only cut e edges at most. Right. All right. So now here we only bounded the expected size of the algorithm's cut. Okay, so we didn't say anything about what is the probability that you get something which is close to e over 2. Okay, yeah, and so therefore, in any execution, there could be a pretty large chance that you get a cut which is much smaller than e over 2. Okay, but as it turns out, this is actually not true. So what you can show is that with very high probability, the algorithm is going to output a cut which is very close to e over 2. Okay, so it's going to be very unlikely that you get a cut which is much less than e over 2. Okay, so you can actually prove this. So we're not going to do this today, but later on we're going to see some analysis techniques which let us prove bounds of this sort. Okay, so that was the first randomized algorithm. So the next algorithm we're going to talk about is quicksort, okay, or randomized quicksort. Okay, so now when you first learn about the quicksort algorithm, so just as a reminder, the way the quicksort algorithm works is that, well, we're trying to sort this array of numbers, right? And what we're going to do is to pick these elements called pivot elements, right? And then the pivot elements are going to split this array into two halves, right? Let's say the left half is going to be all of the values in the array which are less than the pivot, and the right half is going to be all the values larger than the pivot. Okay, and so in this example that I'm showing, right, the pivot element are going to be these red elements. Okay, so if we use 8 as a pivot, right, then we split this array into like all these values which are less than 8, right, and then all these values which are bigger than 8, and then we keep doing this recursively. Okay. Right. So now the question is, how do we pick these pivot elements? Okay. So so usually when people talk about quicksort, one possibility is just to pick the first element in the array as the pivot element. Okay. So that's what we're doing in this example over here. Okay. All right. However, just simply picking the first element, you can actually sort of get in trouble sometimes if you do that. Okay. Meaning that quicksort can run very slowly if you always just pick the first element as the pivot element. Okay, so for example, let's do an analysis. Let's let t of n be the time to quicksort n numbers. Okay, so usually t of n in practice is small. Okay, it's going to be something like n log n in practice, but in the worst case, it can actually be order n squared. Okay, and this can happen when you have very uneven splits. Okay. Meaning that if you pick as your pivot element a number which is either very small or very large. Okay, so for example, if it's very small, then almost all of the other elements are going to be bigger than the pivot, and they're all going to go onto the right side. Okay, so if you pick the pivot, which is, let's say, the smallest element, okay, then the time complexity is going to be the time to quicksort n numbers is going to be the time to do one number, right, plus the time to do n minus 1 numbers, okay, because all of the other n minus 1 numbers besides the pivot are going to go on the right side, okay, plus you need to spend another n minus 1 time just to partition all of these elements, okay, and so if you have a recurrence of this form and you solve it, you're going to get that t of n is order n squared, okay, so so that's quite bad, okay. On the other hand, if you pick a pivot which is near the middle of this of the set of numbers, okay, then you can show that quicksort is only going to take n log n time. So in fact, you don't have to pick exactly the middle element as your pivot. Okay, you can pick something which is close to the middle. So for example, even if your pivot element is in the middle half of the values, okay, so let's say that it's larger than n quarters of the value, okay, 1/4 of the values. And it's also less than 1/4 of the values. Okay, so it's somewhere within the middle half of all of these values. Okay, then your recurrence is going to come out to be t of n is going to be at most the time to sort the left half, which is going to have at most n quarters of the values, right? Plus the time to sort the right half, which is going to have at most 3/4 of the values. Okay, plus the partition time. Okay, and if you have this expression and you solve it, this actually is going to solve to n log n. Okay, so this shows that if we can somehow implement quicksort so that the pivot is always near the middle, okay, or usually near the middle, okay, then we're going to get this good performance. Okay, but then how do we ensure that the pivot is near the middle? Okay, because if you just pick, let's say, your first element as the pivot, right, then you really have no control over where that element falls. Okay, it could be in the middle, but it could also be one of the like smallest or largest elements. Okay, so the way that we're going to ensure that we can pick these middle elements is that we're going to do randomized quicksort. Okay, so we're going to, instead of picking one particular value, for example, the first value in the array as the pivot, we're going to pick a random value. Okay, now if you pick a random value, then intuitively, if you just want this value to be, let's say, in the middle half of all of these values, okay, well, if you pick a random value, you've got a 1/2 probability of this happening. Okay, and if this happens, right, then you get this sort of time complexity, and then you get good performance. Okay, so this is why sort of intuitively this randomized quicksort should work better than deterministic quicksort. Okay, so again, the algorithm is to pick a random element as your pivot. Okay, and then you're going to partition the array into two sets: the one smaller than the pivot and the ones bigger than the pivot, right? And then you're going to recursively randomly quicksort the two halves, or the two sides. Okay, so now let's actually do analyze the time complexity, the expected time complexity for a random quicksort. Okay, so so by the way, so this is going to be a Las Vegas algorithm because it's always going to produce the right answer. Okay, however, it's not always going to run in the same amount of time. Okay, so yeah, so therefore, what we want to do is we want to analyze the expected running time of randomized quicksort. And we want to make sure that this is small. Okay, so to analyze the expected running time, well, what we have is that, so we're going to look at all the possibilities when we run this algorithm. Okay, so one possibility is that we pick a pivot which is the smallest element. Okay, so we're going to say that it's got rank 1. Okay, it's the smallest element. Okay, now if, so this is very bad for us. Okay. And because if this happened, then the running time would be equal to the time to sort the n numbers would be the time to sort the one number, right, the pivot, right, plus the time to sort all of the other, the remaining n-1 numbers, right, plus the time to do the partition, which is n-1, okay, right. However, this bad thing, right, this bad event of picking the rank 1 element as our pivot, this happens with pretty low probability, okay? Only 1/n, right? Because there's only a 1/n probability that you happen to pick the smallest element as your pivot, okay? Now, it's also possible that you pick the second smallest element as your pivot, okay? So if that happened, then the running time would be R of 2, right? Because you have like 2 elements on the left and then n-2 on the right, okay? But again, this also happens with small probability, 1/n, okay? And so, in fact, you can just keep doing this. You can say that, I can pick the rank k element, so the kth largest element as the pivot, okay? And then my running time is going to be like this, and the probability of this happens is 1/n, okay? Because there's just a 1/n probability I happen to use the kth largest element as my pivot. Okay, so therefore, the expected running time is going to be, well, with 1/n probability, we're going to have this running time. Right? With 1/n probability, we're going to have this running time, okay, and so on. And so if we add all these together, then we can have that the running time is going to be just the sum, this sum over here, okay? And the sum is going to simplify a bit because, so for example, each of these terms is going to occur twice, okay? It's going to occur once as R1 plus R of n-1, and then it's also going to occur symmetrically as R of n-1 plus R1. Okay, so each of these terms occurs twice. And then so we can multiply, we can put a 2 over here, right? So we get 2/n times the sum of all of these R values, right? For k equals 1 up to n-1. Okay, plus each one of these terms has this n-1 thing over here. Okay, so we have another n-1 over here. Okay, so we have that the expected running time is equal to this sum. Okay, so now let's just figure out what the sum is. So So in fact, in the end, we're going to show that this sum is going to be bounded by some sort of a log n, n log n term times some constant a here plus b. Okay, and we're going to eventually figure out what these constants are. Okay, but before we do that, we're first of all going to have a little lemma here. Okay, so this lemma is going to help us add up terms of this form. Okay, k log k, for k from 1 to n minus 1. Okay. And basically, this is going to come out to something like 1/2 n squared times log n, okay, minus this other term. And I'm not going to go through all of this algebra here. You can check it yourself. But basically, the idea is that each of these, we're going to take this sum, which has n minus 1 terms, okay? And we're just going to split this into 2 halves, into the lower half, right? So up to this point, and then into the upper half, okay? Right, and then we're going to say that for the lower half, right, they're going to get each of these k terms is going to get multiplied by log k, okay, but here k is going to be at most n over 2, okay, so so therefore log k is going to be at most log n minus 1, okay, and then so therefore you can take this log n minus 1 and you can just pull it out, okay, and multiply by this. Okay, and here the idea is similar. We're going to multiply each of these terms by log k, right? But but here k is going to be at most n minus 1, and so therefore each of these terms is going to be less than or equal to log n. Okay, so therefore you can just take the log n, you can pull it out. Okay, so that's going to simplify our sum a lot, because now we're just left with the sum of k from 1 to n minus 1. Okay, and we know how to do that, and so we just do some more algebra, and then we get that. So then we get this lemma. Okay, so once you have the lemma, then now you can use it to show the expected complexity for randomized quicksort. Okay, so we said that the expected complexity is going to be have this form, right? It's going to be the sum of all of these complexities. Okay. And we said that we're going to guess that this R term here is going to be something like, it's going to be order of k log k. Okay, in fact, we're going to put in the actual constants here. We're going to put an a here and a b over here. Okay. All right, so now we need to evaluate the sum. Okay, and to do that, we're going to use our previous lemma, which lets us compute this sum. Okay, the sum of k log k. Okay. Yeah, and then so this is from the previous lemma, right? So this step over here is from the previous lemma, and then we can do some simplification, and we're eventually going to end up with this term over here. Okay, so this is almost what we want, right? Because we want to show that the time to sort n numbers is going to be at most a times n times log n plus b, but we have this additional term over here. However, we can make this additional term go away if we can just, so all we need to do is just ensure that, this term here is non-positive, okay? And to do that, all we need is that, we need a divided by 4 times n to be at least theta n plus b. Okay, so whatever, so, this theta here has some constant, okay? So whatever this constant is, we're just gonna pick a big enough so that this statement occurs. Okay, for large enough n, for n at least 1, let's say. Okay, right, and then this shows, so then this gives us the complexity for R of n, okay, which is going to be basically, it's going to be theta n log n. And this is what we expect, because we expect that quicksort on average is going to take n log n. Okay, and what we can show is that if you pick these random pivots, right, then indeed the expected running time is going to be n log n. Okay, so those are some simple applications for for randomized for some randomized algorithms. So now we're going to look at another very common application of randomization, which is in hashing. Okay, so you guys have probably seen hashing before, but let's just do a brief reminder of how hashing works. Okay, so so a hash table is it's a random it's a data structure. Okay, but today we're going to talk about a randomized version of a hash table. Okay, and what it does is that it can implement a dictionary. Okay, so the dictionary data structure has to support the following operations. You have to support find, insert, and delete. Okay, so we have a bunch of keys that we want to put into this dictionary. Okay, we have to be able to insert keys and also delete keys, and then also we have to be able to search for keys. Okay, and a hash table, if it's well designed, it can actually do all of these operations in constant time. Okay. However, one problem with the hash tables is that in the worst case, if we don't design this this hash table well, then all of these operations can take order n time, where n is the number of elements in the dictionary. Okay. However, what we're going to show today is that by using randomization, we can make sure that the worst case is very, very unlikely to occur. Okay. And so on average, the running time is going to be order 1. Okay, so one thing is that if hash tables are so nice, right? If they can run in constant time in expectation, right? Then why do we need all these other data structures like binary search trees and heaps and so on? Okay. Well, the problem with a hash table is that it actually doesn't support many functions that we find are useful. Okay, so for example, we don't have any efficient way of finding the minimum or the maximum element in a hash table. Okay, and then also, given one particular element, we can't efficiently find the predecessor or successor to that value. Okay, so the predecessor is the value which is less, the biggest value which is less than your given value. Okay. And then successor is like the next value, right? So it's the smallest value, which is larger than your given value. Okay, so so the hash table can't actually do these operations efficiently, right? You would have to basically scan through the entire hash table to do these operations. Whereas things like binary search trees, right? They can support these min and max and predecessor functions efficiently. However, if the only operations that you want are to insert and delete elements and to find them, right? Then, then hash tables are a very good solution. Okay, so now the simplest way to implement a hash table is that now we're trying to store a bunch of keys. Okay, so suppose the keys have a bounded bounded range. Okay, so in fact, suppose the keys are just numbers, and the numbers are, so in fact, they're going to be integers, okay, positive integers. So we're making a lot of assumptions here, okay? But suppose all of your keys are numbers between 0 to n minus 1, okay, integers between 0 to n minus 1. Then one way that you can implement a hash table is that, well, you can just use an array of size m, okay? So for example, let's say that all the numbers you're trying to store are between 0 to 99. Okay, so you have m equals 100, so all the numbers are between 0 to 99. So then you can just use an array of size 100. Okay, and then now if you want to store a key, well, the key is just going to be a number between 0 to 99. And so since you have a hash table of size 100, you can just put that key exactly into, you can put the key k into position k in your array. All right, and then now if you want to do the find operation, right, then just go to position k in the array, and then if there's a value there, then just return that value. Okay, and otherwise there was no key for that position. And if you want to delete something, right, then again just go to position k and then delete the value there. Okay, so of course now all of these operations take constant time. Okay, so that's very good. But the problem is that if m here is very large, okay, so if the set of possible keys is very large, then since you're using an array of size m, you're going to need to use a lot of storage. Okay, so as an example, suppose your keys are simply 32-bit numbers. Okay, so those are in fact not very large keys, right? So the values are going to run from 0 to 2 to the 32nd minus 1, okay, which is something like 4 billion, okay? So, so now if you want to use this method, so this is called direct addressing, by the way, I forgot to mention this, right? So if you use direct addressing, right, then you need an array of size equal to 2 to the 32nd minus 1, okay? So you need like 4 gigabytes of memory or maybe 16 gigabytes of memory or something like that, okay? So, so it's a very large amount of memory, okay, even for these 32-bit keys. And if you have larger keys, like 64-bit keys, right, then you would need an array of size 2 to the 64 minus 1. Okay, and that's probably more memory than exists in the whole world. Okay, so the main problem with this direct addressing is that you need a very large array to store these keys in. Okay, and in fact, if you want to talk about other types of keys, like say string-based keys, okay, then it's not even clear how to use this direct addressing. Yeah, and then also, even if you the size of your universe is small, right? So let's say that the universe is like 0 to 99. Okay, if you're only storing a few values, right? If you're only storing like 5 values, okay, well then 95% of your hash table is being wasted. Okay, so direct addressing has a bunch of problems, and so hash tables are a way of addressing these problems. So hash tables are similar to direct addressing, but they're going to use much less space. Okay, and so the basic idea is that if you have a key, then instead of storing this key directly at the location equal to the key, right? So that's what you did for direct addressing, right? Whatever your key is, you just put it exactly at that location. Okay, and then the problem there was that the key can be very large, so you need lots and lots of space for this. Okay, but for a hash table, we're going to convert the key to a much smaller value. Okay, and you're going to store it at that location. So for example, even if you have a 64-bit key, okay, we're going to convert it to, let's say, an 8-bit value. Okay, and then we're going to store it at a location corresponding to that value. Okay, so instead of using 2 to the 64 amount of storage, right, now you only need 2 to the 8 amount of storage. Okay, so more concretely, we have a hash table. So it's going to consist, again, of a universe U of keys. Okay, so we're going to need to use this notation later, which is why I'm sort of defining everything right now. Okay, so we have a set of possible keys, which is this big U, right? We have an array which is being used to implement our hash table. Okay, so let's call the array T, and let's say that this hash table has this array has size M. Okay, and then we also have a hash function H, which is going to take a key, right, and then map it to one of the locations in the hash table. Okay, so since the hash table only has size M, it's going to map it to a value between 0 to M minus 1. Okay, any key gets converted to one of those values. Now, of course, the key part is how do we pick these hash functions? Okay, so we're going to look at several ways of picking these hash functions later. Okay, but first, let's assume that we have one of these hash functions. Then the way things are going to work is that if we want to insert a key and a value for that key, right, then we're just going to take this key and then pass it through the hash function. Okay, so the key comes from the universe U, and after you apply the hash function to it, you're going to get a value between 0 to M minus 1. Okay, so that's going to correspond to one of the locations in the table. And so now you're just going to store this value V at this location in the table, at location H of K. All right, so for example, in this diagram over here, right, if you have a key K1, you're going to apply the hash function to get a location H of key 1, right, and then you're going to store that value exactly at that location. Okay, if you want to find a value, right, then again, you're going to hash the, find a key, then you're going to hash the key, and then you're going to go look in the array at that index. Okay, and if you want to delete a value, or sorry, delete a key and its value, right, then you're going to again hash the key, right, go to that index, and then just delete any value there. Okay, so so now these hash functions, we haven't talked about how to define them, but usually you can define them in a pretty simple way. Okay, so these hash functions are cheap to compute. In fact, oftentimes they only take constant time to compute. Okay, so in that case, you can see that all of these operations over here, since they only involve hashing the key and then going to an array index, right, they all take just constant time. Okay, and also the amount of storage that you use is going to be order M, right, because you simply have an array of size M. Okay, and now you can pick M to be much, much less than U. Okay, for example, you could have 64-bit keys over here, but you can have an array of size, let's say 256. Okay, so m is going to be much, much less than u, so therefore this hashing is going to use much less space than direct addressing. Okay, now the only downfall to this technique over here is this thing called collisions. Okay, so collisions is what is when, let's say that you have two keys. Okay, and let's say that when you apply the hash function, they both produce the same value. Okay, so they have the same index, so they go to the same index in the hash table. Okay, so now the problem is that each of these keys has a different value. All right, it's associated with a different value. Okay, and each of these locations can only store one value. Okay, so now we're trying to store two different values at the same location. Okay, so so this is called a collision, and we need to figure out what to do. Okay, now collisions are in fact unavoidable if your universe is larger than your hash table size. Okay, so for example, if you have 100 potential keys, right, and your hash table only has size 10, right, then I can always find two different keys that go to the same location. Okay, right, because otherwise, if you want every key to go to a different location, you can have at most 10 keys. Okay, so yeah, so we need to somehow deal with these collisions. Okay, and there are two basic methods: close addressing and open addressing. Okay, so today we're just going to briefly review close addressing because close addressing is going to be we're going to use some of these ideas for close addressing when we talk about universal hashing and perfect hashing. Okay, so for closed addressing, yeah, what we're going to do is that suppose you have several keys that map to the same location, that hash to the same location. Okay, then at that location, we're going to store all of these keys and their values. And the way you store them is using a linked list. Okay, so for example, over here, right, we have three keys, right, K2, K5, and K7, right? They all go to this, they all hash to the same index. Okay, so then we're going to store three different values over here. Okay, and we're going to store these values using a double-sided linked list. Okay, and now if you want to add a value into the hash table, then again you're going to first of all hash this key, right? And that's going to take you to a location. Okay, and at that location you could either the location could be empty, right? So for example, if you hash to this location is empty, and in that case you can just store the key and the value there. Okay, you can make a new node, and then you can put a pointer over here and then store the key and the value. Okay. However, if you hash to a different location, right? So suppose you hash to this location over here. Okay, then you're going to put you still want to store your key and value, and the way you do that is you just add your key and value to this linked list. Okay. All right. So next, if you want to find a key, then you're first of all going to hash it. Okay, and then that's going to take you to an index. And at that index, you could have a linked list, okay? And your key could be anywhere within that linked list, right? Or it could be not in the linked list, okay? But you're going to have to go through this entire linked list to find out whether your key is at that location or not. And then if you want to delete a key, right? Again, you're going to hash the key and go to an index, and then for the linked list at that index, you're going to delete the key from that linked list. Okay, so now, so these different linked lists can have different lengths. Okay, so suppose that this n hat here is the length of the longest linked list. Okay, and then let's say that on average, these linked lists have size m bar. So then in the worst case, right, if you happen to have a key which hashes to this longest linked list, then whenever you do a find, for example, okay, you're going to have to go through this entire linked list. Okay, and that's going to take you order n hat time. Okay, on the other hand, if you have, let's say, a random key, so a random key is going to hash to a random location, and a random location has, so the length of a random location is going to be m bar by definition. Okay, so therefore with a random key, you're going to have m bar running time. Okay, so next we're going to define the load factor. So you see that the longer your linked list, right, the worse your running time is. Okay, whether it's on average or it's in the worst case. So what we want is we want to make sure the linked lists are not too long. Okay, and to do this, we want a hash function which appears random. Okay, so what this means is that if you give it any key, okay, then this hash function is equally likely to put this key into any location in the table. Okay, so it appears to put the key into a random location. All right, so the reason we want this is that suppose you have a hash table with n items in it, okay? And then suppose the hash table has size m, okay? So let's say that you have a hash table of size 100, and let's say you've already put 200 items into the hash table. Okay, then if we have this uniform key assumption, meaning that any key gets put into a random location, okay? Then on average, since you have n items and you have m possible locations for each item, right? Then on average, each location is going to have n divided by m keys in it. And we're going to call this n divided by m the load factor. Okay, and we're going to use alpha to denote the load factor. And we want the, right, so if you have a load factor of alpha, then the average time for each operation is going to be order alpha. Okay, because you, on average, you're going to have to search through a linked list of size alpha. And of course, we want this alpha to be small. Okay, so you don't want to put too many items into your hash table. Okay. However, the problem is that even if you have uniform hashing, okay, it is still possible in the worst case that all of your keys can hash to the same location. Okay, because we're going to I think I didn't mention this, but I need to say this, which is very important. So here we're using a hash function which appears random. Okay, this does not mean that the hash function actually is random. Okay, so the hash function has to be a deterministic function. Okay, and so if it's a deterministic function, then kind of like the same way we talked about, if you remember the first problem we had where you had a string of half A's and half B's, right? And you could force any deterministic function, deterministic algorithm which was trying to find an A, you can always force it to just only see A's at the beginning, or only see B's at the beginning, right? Well, in the same way, if you have a deterministic hash function, you can force it that I can always produce a set of keys such that all of these keys hash to the same location. Okay, so so if I have n keys and they all hash to the same location, then this algorithm is going to take order n time. Okay, instead of order n divided by m time. Okay, yeah. So so now we're going to talk more about how we're going to find these hash functions. Okay, so we said that we want the hash functions to hash keys to quote unquote random locations. Okay. However, the hash function cannot be random itself. Okay. So the hash function must be a deterministic function, meaning that if you apply, if you compute h of k, okay, for a key k, then this always has to return the same value. Okay. So a deterministic function is always going to return the same output for the same input. Okay. And we need to have this property because suppose h of k was actually non-deterministic. Okay, so if you run this function twice, let's say it can produce different values. Okay, but then you can't use it to do a hash table because let's say if you use it to do a hash table, right, then the first time that you put something into the hash table, you're going to put it at location h of k. All right, and next time, let's say you go look for that key. Okay, and then if you apply the hash function again, and if it's non-deterministic, then the second time you apply h, you can get a different location. Okay, and at that different location, you're not going to find k, right? Even though k is in the hash table, you're not going to find it unless h of k always returns the same value each time, given the same input. Okay, so therefore we need the hash function itself to be deterministic. Okay, even though you want it to appear random. For example, you want the hash function to take a key and then have sort of equal chance of putting it anywhere within the hash table. Okay, so it's actually kind of hard to find these sort of functions which are both deterministic and yet they appear to be random. Okay, and also since we don't assume anything about the distribution of the input keys, right? Then this makes it even harder to find one of these so-called random hash functions. Okay, so in fact, you can pick any function. Okay, any hash function from u to m. Okay, so there are always going to be at least u divided by m keys from the universe that hash to the same location. Okay, so this is like the pigeonhole principle. Okay, so therefore, if you happen to have your input is exactly this set of inputs, this set of keys. Okay, these u divided by m keys that hash to the same location, right? Then all of these keys are going to go to the same location, and so now all of your operations are going to take this worst case order n time. Okay, and because we don't assume anything about the input distribution, then we can't really claim that this won't happen. Right? It is possible for this to happen. Okay, but usually we expect in practice that we're not going to be very, very unlucky and just happen to get this worst case input. Okay, and so therefore, usually in practice, we can assume that we get pretty good behavior using just heuristic hash functions. Okay, so for example, heuristic hash functions are well, first of all, let's say that so the keys are natural numbers. Okay, and if your keys are not natural numbers, then you can convert them to natural numbers. So for example, if your keys are strings, okay, then you can convert these strings to a number. Okay, like for example, if you have a string pt, okay, then you can represent each of these letters using an ASCII number, right? So using a number from up to 128, right? And then you can just convert this pt, right? So p is like apparently the 112th ASCII letter, right? And so you multiply that by 128, and then you add this to t, which is apparently the 116th ASCII letter. Okay, and this converts it to a number, the string to a number. Okay, so then we might as well assume that all of the keys are just natural numbers. Okay, so so one way that we can implement a hash function, so the simplest way is using something called the division method. Okay, so this is just going to take this key, right, and then take it modulo m, where m is the table size. Okay, so that's going to get us an index between 0 to n minus 1. Okay, and usually we're going to choose m, so we get to choose the size of our hash table, right? And so usually we choose m to be a prime number which is not close to a power of 2. Okay, so there's no, I mean, this is not guaranteed to work well, but in practice, this is how people choose this. Okay, so that's called the division method. There's also something called the multiplication method, which is we're going to take the key and we're going to multiply it by some constant. Okay, so this constant here can be a real number, or actually it's going to be a fractional number. Okay, and then so this k times a is also going to be have a fractional part, and we're just going to keep the fractional part. Okay, we're going to take a modulo a, meaning we don't ignore the integer part and just keep the fractional part, and then you're going to multiply this by m. Okay, and then you take the floor of that, and again, this is going to produce a number between 0 to n minus 1. Okay, so we can pick a to be basically anything we want, but there was a suggestion by Don Knuth to pick a be equal to this. Ooh, sorry about that. Okay, so his suggestion was to pick this number. Okay, so I'm not sure why he why he made this suggestion, but anyways, you can go look up his reason for doing this, okay? And if you do this, right, then by taking different keys and multiplying by this, this a over here, right, and then taking the fractional part, okay, and then you multiply by m, the table size, then this will let you produce any number between 0 to m minus 1. Okay, right, now all of these methods are just heuristics, okay, so they're not guaranteed to work well, okay? So now we're going to look at something called universal hashing, which is going to say that, so for the previous heuristics, we can always choose an input. So we can play the role of the adversary. So if you remember the lecture on lower bounds, right? So the adversary is some guy that's trying to make your algorithm have a tough time. Okay, it's trying to make life as hard as possible for the algorithm. So this adversary is going to pick a set of inputs, and that's going to make your algorithm run as slow as possible. Okay, and as long as you pick a deterministic hash function, the adversary can always do this. So universal hashing is going to be a way to overcome this. Okay, it's going to make sure that the operations on average are not going to take order n time. They're going to take order n divided by m time in expectation. Okay, n is your number of elements, m is your hash table size. Okay, and it's going to do this using randomization. Okay, and also note that this n divided by m is optimal, right? Because on average, each table location is going to have on average n divided by m items in it. Okay, so if we simply take n divided by m time in expectation, this is the best we can do. Okay, so the way that universal hashing does this is that it's not going to use a fixed hash function. Okay, if you use a fixed hash function, the adversary can always make your life hard. Okay, I can always ensure this happens. Okay, instead, universal hashing is going to have a bunch of hash functions. Okay, so it's going to create, like, let's say 1,000 hash functions. Okay, and let's call this collection of 1,000 hash functions, let's call that capital H. Okay, and then it's going to use a random hash function out of this collection of functions. Okay, right, and then we want this collection of hash functions, which is called a universal hash family. Okay, so this H is going to be called a universal hash family if it has the following properties. Okay, so if we take any two keys, X and Y, okay, any two different keys, okay, then if we pick a random hash function out of this family capital H, okay, and then you apply X and Y, you apply this hash function to X and Y, then the probability that they collide is going to be 1 divided by m being your table size. Okay, so this is like the best possible, right? Because each of these things is going to go to one of these m possible locations, right? So the minimum collision probability is going to be 1 divided by m. And the universal hash family is going to achieve this if you pick a random hash function out of this family. Okay, yeah. So therefore, the way that we're going to use universal hashing in practice is that now you're going to give me a set of keys, okay? And then so previously, if I use a fixed hash function, right, then the set of keys that you give me can always be these worst case keys that makes the hash function take order n time. Okay, but now since I have a bunch of different hash functions, okay, let's say I have 1,000 different hash functions, okay, and now you don't know which hash function I'm going to use. Right? And so you give me a set of keys, and then it could be that for some of these hash functions in this family H, then the hash function doesn't work well for your keys. Okay, so I get lots of collisions, right? And things are slow. But for some other hash functions in my family, they might work well. Okay, so I get very few collisions. Okay, and because you as the adversary don't know which hash function I'm going to use, right? Then you're going to give me some set of n inputs, and afterwards, I get to decide which hash function I use. Okay, and I'm just going to use a random one. And by using this random hash function, I'm going to make sure that I get good average performance, right? N divided by m performance. as opposed to order n performance. Okay, now I just want to mention again that the hash functions themselves, okay, all the hash functions in this family capital H, none of them are random, okay? All of them are deterministic functions, okay? What's randomized is that we're going to pick a random one of these hash functions to use, okay? And then once we pick that hash function, we have to use the same hash function for all of the keys, right? We can't use different hash functions for the keys, okay? So yeah, so you give me the keys, right? And then I make a random choice and pick a random hash function, and then I use that function for all of your keys. Okay, so now suppose you have a universal hash family. Okay, we're going to prove some properties about this thing, and then we're going to talk later about how do you actually construct a universal hash family. Okay, but the first property we're going to show is that if you have a universal hash family, and then you have a set of n keys, okay, and then you pick an element x in your from your keys, okay. Then if I select a random hash function, then the expected number of other keys from your set S that collide with this fixed key x, okay, the expected number of such keys is n divided by m. Okay, so the way we're going to show this is that suppose your set S is going to have n keys in it, okay, and let's let this random variable capital X be equal to the number of other keys in S that collide with X, okay. So so therefore x of I is going to be and we're going to set x of I to be 1 if the ith element in your set collides with x using this hash function h, okay, and otherwise it's 0. Okay, so then the expectation of this random variable is just going to be the probability that a random element collides with x, okay, right? And we said that, and because this is a universal hash function, universal hash family, then we're going to pick a random hash function. And under this hash function, the probability that x of I collides with x is just going to be 1 divided by m. Okay, so each of these xi's has an expected value of 1 divided by m. And so therefore, the expected number of items that collide with little x, right? So the expected value of capital X here is just the sum of all of these individual expectations, right? And there are n of these over here. So this is going to be equal to n divided by m. Okay, so next we need to talk about how to construct a universal hash family. Okay, all right. So so the way we're going to do this is that we're going to pick a prime number p. Okay, and this p has to be larger than the hash table size, right? So p is larger than m, and p should also be larger than all of the keys. Okay, so if you have, let's say, 64-bit keys, right, then we should pick a larger prime number. Okay, more than 64 bits. Okay, and we have various efficient ways of selecting such prime numbers. Okay, all right, and now we're going to define this function, this hash function h sub ab of k. Okay, so I'll tell you later what a and b are, but so these are just going to be a and b are going to be constants. Okay, and the way this hash function works is that given a key k, we're going to multiply by a and then add b. Okay, and then we're going to take this modulo p, okay, this big prime here. We're going to take a modulo the big prime, right? And then we're going to take another modulo this table size here, modulo m. Okay, so now this is going to produce a value between 0 to m minus 1, and that's going to be one of the locations in our hash table, right? Our hash table has size m. Okay, so for every a and b, we can define such a hash function like this. Okay, now in order to define our universal hash family, what we're going to do is we're going to select all possible choices for a and b, okay, where a is going to be a number between 1 to p minus 1. And then b is going to be a number between 0 to p minus 1. Okay, so in total, we have p times p minus 1 different hash functions in this hash family. And now the claim is that this is a universal hash family. Okay, so now we're going to prove that this hash family H sub Pm, okay, right? Because this depends on P and this depends on M, so we're going to call this H of Pm. We're going to claim that this is a universal hash family. Okay, so all right. So to do this, let's just pick two keys, okay, x and y, all right? And we know that since p is larger than all the keys, we know that x and y are both less than p. All right, so now we're going to pick a random one of these hash functions, HAB, right? And the first thing we're going to do is, so we're going to take two mods when we compute HAB, okay? So let's first consider the inner modulo part. Okay, so we're going to take, for a key x, we're going to compute ax plus b modulo p, and let's call this r, right? For y, we're going to compute ay plus b modulo p, and we're going to call this s. Okay, so the first claim is that r is not equal to s. Okay, and this is because if you do r minus s, okay, then this is congruent to a times x minus y modulo p. Right? Because all we're doing is you're just taking ax plus b minus ay plus b, right? And then you take that modulo p, okay? And now this value here, this is not going to be 0, okay? And the reason is that a is not going to divide p, right? Because a is going to be in the range 1 to p minus 1, and then p is prime, so a doesn't divide p. And then also x minus y, right? Both x and y are less than p, so x minus y is also not going to divide p. Okay, so therefore, this whole thing is this a times x minus y is not going to divide p, and so therefore this thing modulo p is not going to be 0, and that shows that r is not equal to s. Okay, so that's the first fact. The second fact is that for each pair AB, okay, if you use different a's and b's, okay, so we're going to fix the x and the y, okay, but you're going to use different a's and b's, okay. For each pair AB, we're going to produce a different pair RS, okay. And the reason this is true is because given a pair RS, right, we can actually figure out which A and B produced this RS. Okay, so in particular, we can, so we have that R minus S equals A times X minus Y modulo P, right? We have this equation over here, okay? So therefore, we can just do R minus S times the inverse of X minus Y. Okay, this is kind of like dividing by X and Y, except for when you're working modulo P, you can't really divide. You can just multiply by the multiplicative inverse of X minus Y, okay? All right, so we can multiply by the inverse of X minus Y, right? And that's gonna get us A over here, okay? R minus S times X minus Y inverse is gonna get us A, right? And then once you have A, right, then now you can figure out what B is, because you can just do R minus AX modulo P is equal to B, right? So we can use this equation over here, okay? So this shows that for any R and S, right, we can produce a unique A and B, which led to this R and S, right? And so this shows that for every A and B, we have to produce a different pair RS, right? Because otherwise, if you have two different pairs, A B and then A prime B prime, that both lead to the same pair RS, right? Then when you apply these two equations, right, you're going to get two different A's. Okay, you're going to get A and A prime. Okay, but that's not possible because all of these things they only have a single value. Okay, all right. So that is the second fact that we need, and so what this shows is that now remember that how many A-B pairs did we have? Well, we have, so A is from this set, right, and then B is from this set. So in total, we have P times P minus 1 different A-B. Different values for A and B, okay? And also for R and S, okay, and each one of these leads to a different RS, okay? So therefore, and R cannot equal S, okay? And so therefore, this is gonna lead to P times P minus 1 different pairs of RS, okay? And so this shows that, and so there's this one-to-one mapping between the AB values and the RS values, right? And this means that if you pick a random AB value, then you're going to get a random RS value, okay? Because there's this one-to-one mapping between the ABs and the RSs, okay? All right, so now we're going to use this fact, and now we're going to look at the collision probability between X and Y. Right, this is what we're trying to figure out, right? What's the probability that X and Y, when you hash them using H sub AB, what's the probability they collide? Okay, so we've established all of these facts, and now we can actually compute this probability. Okay, so the probability that X and Y collide is equal to the probability that R is congruent to S modulo M. Okay, because remember the way this hash function works is that let's erase a few things so that you can see things more clearly, okay? The way this works is we're first of all going to compute this R value and this S value, right? That's this part over here. And then you're going to take things modulo M, right? So in order for R and S to produce the same hash value, then they have to be congruent modulo M. Okay, now for any fixed R value, the number of different S values which are not equal to R, okay, because remember that R is not equal to S, okay, but which are congruent to S modulo P, right, modulo M, is going to be, well, there are P values, P possible values for S, okay, and so, so the number of such values where this holds is going to be P minus 1 divided by M. Okay, so then for each R and a random S, okay, then since there are only P minus 1 divided by M values S where this relationship holds, okay, then for a random S, the probability that this relationship holds, right, is going to be the number of values, the number of S's such that this relationship holds, divided by the total number of S values which are not equal to R. Okay, and this is going to come out to 1 divided by M. Okay, so this shows that the probability that X and Y collide is equal to the probability this happens, which is equal to 1 divided by M. Okay. Yeah. So therefore, for any keys X and Y, right? If you pick a random HAB out of this this hash family, then they collide with 1 over M probability. Okay, and this shows that this hash family here is universal. Okay, right now we're going to talk about one final topic, which is perfect hashing. Okay, so so the hashing methods that we have up to now, they can produce like constant time expected performance. Okay, but in the worst case, there's still going to be order n. Okay, even though for universal hashing we have that in expectation, it's going to be order n divided by m. Okay. Now, we can actually do better than in expectation order n divided by m. Okay. What we can do is we can guarantee that there will not be any collisions when we use perfect hashing. Okay. However, for perfect hashing, we have a restriction that we need to first of all fix the set of keys. Okay. So you give me a set of keys, right? And then I'll find for you a hash function which has no collisions at all. Okay. So that's what perfect hashing is, right? There's no collisions whatsoever. So it's perfect. Okay, but here you have to tell me what the keys are ahead of time. So therefore, perfect hashing can only implement a static set. Okay, it can implement a set where you can find things and you can delete things, but you cannot insert additional items. Okay, so this would be useful in some cases because, for example, we have certain read-only mediums, right? So we have like DVDs and Blu-ray discs. Okay, so those things you can't really write to them, right? I mean, you have rewritable DVDs, but if you're talking about like a DVD that you bought from the store, right? Those are not rewritable, and so if you want to store a set of keys on this on a non-rewritable medium, then you can use perfect hashing. Okay, so how does this work? Well, suppose we want to store n items, okay? We want to have no collisions whatsoever. Then the way perfect hashing works is that we're actually going to use 2 levels of universal hashing, okay? Right, so the first level is going to have a hash table of size m equals n. Okay, so you're trying to store n items. Okay, so for example, in this example over here, they are trying to store 9 items. Okay, so we're going to have a 2-layer hash table. The first layer is going to have size equal to the number of items. Okay, so size 9 in this example. Okay, and now in the first layer, we're going to have just a hash function. Okay, and the hash function is going to come from a universal hash family. Okay, and it's going to hash each key to a location in this hash table here of size m. Okay, m equals n. Now, at each of these locations, we're going to have another layer of hashing. Okay, so we're going to have a hash table at each one of these locations in the first layer hash table. Okay, and for each of these hash tables, these second layer hash tables, we're going to use a different hash function. Okay, so at location j, we're going to have a special function s of j. This hash table at location j is going to be called s of j, and then the hash function that we're going to use at that location is going to be called h of j. Okay, and now we haven't said how big this s of j hash table is. Okay, so what we're going to do is we're going to look at how many keys actually hashed to location j when you apply the first layer hash function. Okay, so suppose n sub j keys hash to the location j. Okay, then we're going to define the size of this s of j, right? This hash table at location j, we're going to define its size to be the number to be nj squared. Okay, to be the number of keys that hash to this location squared. Okay, and then in order to insert items, right? So then what we're going to do is in order to insert a key, you're first of all going to use the, let's say that this is our first layer hash function. Okay, so you're going to use this function to find a location, and then at this location, you're going to apply another hash function, h sub j, to find the location within the second layer hash table where you're going to store this value. Okay, so in this example over here, right, we have that, and all of these hash functions come from a universal hash family. Okay, all right, so in this example here, we have that, there's only a single value that hashed to location 0 over here. Okay, so therefore you're going to set the size of this table to be just 1 squared, right? And then the hash function, let's say that you happen to use 0 and 0 for this h function over here. Okay. Now over here, you have 3 different values that hashed to this location. Okay, so you're going to set the size of this hash table to be 3 squared, to be 9. Okay, and you're going to use a hash function, which is going to have, these universal hash functions, these hash functions from the universal hash family is just going to have the form that we talked about previously. Okay, the ak plus b modulo the, the prime modulo the table size. Okay, and here we're going to set a and b to be 10 and 18. Okay, yeah, so this is how we implement the hash function. Okay, and what we're going to ensure is that there are no collisions. So there can be collisions in the first layer hash table, right? So for example, we have 3 different values here that hash to the same location in the first layer hash table. However, we're going to ensure that in the second layer hash tables, okay, there are no collisions at all. And because of this, then now we can ensure that all of the operations are just going to take constant time, right? Because you simply need to apply the hash function twice, okay, which takes constant time. Now, the question is, how much space is this going to use, okay? And it turns out that this is going to use space which is equal to m plus this thing over here, right? Because we need to use m space for the first layer hash function, right? And then for the second layer hash functions, each of them has size nj squared, right? And we have m of them, so the space for the secondary hash functions is just the sum of these nj squareds. Okay. Now we want to make sure that this overall space usage is not too large. Okay, because if you use a very, very large hash table to store just a few items, then it's easy to get no collisions. Okay, but what we're going to ensure is that this total amount of space, okay, is only equal to order n. Okay, where n is your number of items. Okay, so we're going to ensure that this entire thing here is going to be order n. Okay, and so since you're storing n items, then even using a normal hash table, you would need to use order n space in order to have constant time operations. Okay, and with a normal hash table, you could have some collisions, right? So some operations can take more than constant time. But with this perfect hashing, we're going to get constant time operations for all the keys, right? And use the same amount of space as normal hashing. Okay, so to do this, we're going to have to prove a few things. So the first thing is that suppose you want to store n keys. Okay, so now this n is different from the n in the previous slide. Okay, so let's just have, so you're trying to store n keys, and now let's say you use a very large hash table. Okay, it's going to have size n squared. Okay, and you're going to use universal hashing in order to store these n keys. Then the claim is that with at least 1/2 probability, you're not going to have any collisions in this big hash table. Okay, and the reason this is true is because with n keys, so you have n choose 2 pairs of keys that can collide. Okay, and now since you're using universal hashing, then each collision happens with probability 1 divided by m, right? Where m is the hash table size. So here we're using a table of size n squared. So the collisions, each collision happens with probability 1 over n squared. Okay, and there are n choose 2 possible pairs of keys that can collide. So therefore, the expected number of collisions is just n choose 2 divided by n squared. And this is going to be less than 1/2. Okay, yeah. And so, so now we can use Markov's inequality, which says that the probability that the number of collisions is larger than 1, okay, is less than or equal to the expected number of collisions divided by 1. Okay, and this is going to be 1/2 by what we just said. Okay, so there's only a 1/2. So the probability that we have any collisions, that we have at least one collision, is going to be at most 1/2. Okay, and so therefore, when you right, so this shows the lemma. And now suppose you want to guarantee that your hash table has no collisions. So then what you're going to do is you're going to use, when you're hashing n keys, you're going to use a table of size n squared, right? And then by universal hashing, you have a probability 1/2 that there is no collision. And if you're unlucky and you actually did get a collision, well, then you'll just try to rebuild the hash table. Okay, you'll choose another hash function from this universal hash family, and you'll rebuild your hash table. Okay, and again, with probability 1/2, you're going to have no collisions. Okay, so therefore, you just need to rehash twice in expectation before you find a hash function which does not cause any collisions. Okay, so now we're almost done here. So we're going to look at the so now we're going to look at the space complexity of this of perfect hashing. Okay, so we're going to store n keys using a first layer hash table of size m equal to n. And then the secondary hash tables are going to have total size the sum of these nj squares, where nj, again, is the number of keys that hash to a location j in the first layer hash table. And we're going to show that the sum of these n squares is going to be less than 2n. It's going to be at most 2n. Okay, so so we have this equality over here, right? So if you want to add up the nj squares, right, then you can just sort of take the sum apart, and you have this expression over here, okay, right? And now you can break the sum into 2 halves. So you have the sum over here, right? So this is by linearity of expectations. So you have the sum of the first part, and then this sum over here. Okay, now we're going to do the second part first, right? So we're going to look at this sum, right? Now this sum is, we claim that this is actually equal to the total number of pairs of hash keys which collide in the first level hash table. Okay, because if you look at, so we have n sub j number of keys that go into location j in the first layer hash table, right? And so all of these keys, all of these nj keys collide with each other, okay? And there are nj choose 2 of these pairs of keys that collide with each other, okay? And now if you take any pair of keys that collide with each other, right, they're going to collide in one of these locations j, right? They have to collide somewhere in the first layer hash table, okay? So they're accounted for when we sum over all of these nj choose 2s, okay? So therefore, this is equal to the total number of colliding pairs of keys, right? And what we know about this is that since you have n keys in total, and there are n choose 2 of these pairs of keys, right, in total, and each one of them has a 1 over m probability of colliding, where m here is equal to n, right? Then the total number of, then the total pairs of keys which collide is, in expectation, it's going to be the product of these two things, which is m minus 1 divided by 2. Okay, right. So therefore, we have that this sum over this term over here is going to be m minus 1 divided by 2, right? And then if you multiply by this 2, then you're going to get m minus 1 for the second term over here. Okay, and then for the first term, well, this is easy because this is just nj is the number of keys that went to location j. And so if you sum over all the possible locations in the first layer hash table, then you're just going to get n, right? Because every one of your n keys had to go to some location in the first layer hash table. Okay? Yeah, so therefore, the overall sum of all of these nj squares, okay, is just going to be this thing over here, which is, it's basically going to be n plus n. Okay, so this is going to be at most 2 times n. Okay, so this shows that these secondary hash tables altogether are only going to use size 2 times n. Okay, and the first layer hash table uses size n, so altogether we're going to use size 3 times n in expectation. Okay, so that is the end of this lecture. So next time we're going to talk about another application for randomized algorithms, which is it's called Bloom filters. Okay, so it's kind of similar to a hash table, but it's both better and worse than hash tables. Okay, so I'll explain that next time. Okay, so see you guys next time.